What if I told you there's a new type of computer on the horizon? A computer so powerful it could change the world as we know it. We're not talking about a simple upgrade here, folks. This is about harnessing the strangeness of quantum mechanics to unlock possibilities we never even dreamt of. This is the quantum revolution, and it's closer than you might think. Imagine a world where diseases are cured before they even manifest, where materials are designed at the atomic level to be stronger, lighter, and more efficient, where complex simulations can predict everything from climate change to the stock market with incredible accuracy. This isn't science fiction, my friends. This is the potential of quantum computing. But before we dive into the how, let's take a step back and understand the what. What exactly is this revolutionary technology, and how does it work its magic? Get ready to have your minds blown because we're about to embark on a journey into the fascinating world of quantum computing. For centuries, we've relied on classical computers to power our world. These machines, while impressive, have limitations. They process information as bits, which can be either a 0 or a 1. Like a light switch, it's either on or off with no in-between. But what if we could harness the bizarre rules of the quantum world to break free from these limitations? Enter quantum computing. Instead of bits, quantum computers use qubits. These qubits have a special ability. They can be in a superposition. Imagine a light switch that can be both on and off at the same time. That's the basic idea behind superposition. It allows quantum computers to perform calculations in ways that classical computers simply can't. But wait, there's more. Qubits can also be entangled. This means that two or more qubits become linked, even when separated by large distances. Imagine two light switches, miles apart, flipping on and off in perfect sync. That's entanglement, and it's another key to the power of quantum computing. By harnessing superposition, entanglement, and other quantum phenomena, these new-age computers can tackle problems that would take classical computers billions of years to solve. It's like comparing a horse-drawn carriage to a spaceship. They both get you from A to B, but the spaceship does it faster, more efficiently, and opens up a whole new universe of possibilities. Think of it like this. Our classical computers are like trying to solve a complex jigsaw puzzle with only a few pieces. Quantum computers, on the other hand, give us access to the entire puzzle box, allowing us to see the bigger picture and solve problems in ways we never thought possible. But how do we control these qubits and harness their power? That's where quantum gates come in. Just like logic gates in classical computing, quantum gates manipulate qubits, putting them through quantum operations to perform calculations. These gates are the building blocks of quantum algorithms, the special instructions that tell quantum computers what to do. Now I know what you're thinking. This all sounds incredibly complex. And you're right, it is. Quantum mechanics is notoriously mind-boggling even for physicists like myself. But the beauty of it is that you don't need to be a quantum physicist to appreciate the potential impact of this technology. In the next section, we'll delve deeper into the differences between classical and quantum computing, exploring how this revolutionary technology is poised to reshape our world. So buckle up and get ready for a thrilling ride into the future. In the world of classical computing, everything boils down to bits. Like a light switch that's either on or off, a bit represents a single piece of information as a 0 or a 1. But the quantum world dances to a different tune. Instead of bits, quantum computers rely on qubits, the building blocks of quantum information. Now here's where things get really interesting. Qubits have this incredible ability called superposition. Imagine a coin spinning in the air, not yet landed on heads or tails. That's superposition. A qubit can exist in a state of both 0 and 1 simultaneously, like a blurry combination of possibilities. This mind-bending property allows quantum computers to explore many different paths simultaneously. It's like having a massive parallel processing system capable of tackling complex problems exponentially faster than classical computers. But it doesn't stop there. Qubits have another trick up their sleeve: entanglement. Section 2, Entanglement, the quantum connection. Imagine two coins flipping in perfect sync, no matter how far apart they are. That's the magic of entanglement. When two qubits become entangled, their fates are intertwined. Measuring the state of one instantly reveals the state of the other, regardless of the distance between them. This interconnectedness is the secret sauce that gives quantum computers their extraordinary power. It allows them to perform operations on multiple qubits simultaneously, exponentially amplifying their computational capabilities. To put it simply, imagine searching through a maze. A classical computer would have to try each path one by one. But a quantum computer, using entanglement, could explore all paths at once, finding the exit much faster. This ability to manipulate and measure entangled qubits unlocks a whole new realm of possibilities for solving complex problems that are practically impossible for classical computers to handle. Section 3. Quantum leap in computation. Think of it like this. Classical computing is like playing checkers, while quantum computing is like playing a multidimensional chess game. The rules are different, the possibilities are vast, and the strategies are far more intricate. With superposition and entanglement, quantum computers can tackle problems that would take classical computers billions of years to solve. From breaking complex codes to simulating intricate molecules, quantum computing holds the key to unlocking solutions in fields like medicine, materials, science, and artificial intelligence. While still in its early stages, quantum computing is rapidly evolving, and its potential impact on our world is nothing short of revolutionary. Now you might be wondering, how does this quantum magic actually work in practice? How do we control these qubits and harness their power to perform meaningful calculations? Well, that's where quantum gates come in, the ingenious tools that allow us to manipulate and orchestrate the quantum realm. Stay tuned as we delve into the fascinating world of quantum gates and explore how they unlock the true potential of quantum computing. Section 1. The quantum realm where rules get weird. So far, we've talked about the amazing potential of quantum computers, but to truly grasp their power, we need to take a peek into the mind-boggling world of quantum mechanics. Now don't worry, you don't need a PhD in physics to understand the basics. Just think of it as a different set of rules that govern the universe at the tiniest level, the realm of atoms and particles. In the quantum realm, things aren't so clear-cut. Imagine a world where objects can be in multiple places at once, where certainty gives way to probabilities, and where particles behave like waves and waves like particles. It's enough to make your head spin. But trust me, it's this very weirdness that makes quantum computing so powerful. One of the key principles of quantum mechanics is superposition. Remember our spinning coin existing in a state of both heads and tails simultaneously? That's superposition in action. In the quantum world, particles can exist in multiple states at once until we try to measure them. It's like they're saying, "Hold my beer. I can be in all these states at the same time, no problem." Now you might be thinking, but how can something be in multiple states at once? That's just crazy talk. And you know what? You're not wrong to think that. Our everyday experiences don't quite prepare us for the quantum world. But numerous experiments have proven that superposition is a real phenomenon, and it's this very principle that forms the bedrock of quantum computing. Quantum superposition embracing uncertainty. Think of it like this. Imagine a single qubit as a spinning coin, but instead of heads or tails, it represents 0 and 1. In superposition, this quantum coin is spinning rapidly, existing in a blurry combination of both states simultaneously. It's not that we don't know the state, it's that the qubit itself hasn't decided yet. Now here's where it gets really interesting. When we measure the qubit, we force it to collapse out of superposition and choose a definite state, either 0 or 1. It's like the spinning coin finally landing on either heads or tails. But before we measure it, the qubit explores both possibilities simultaneously. This ability to be in multiple states at once is what gives quantum computers their incredible computational power. It's like having a massive parallel processing system, allowing them to explore many different paths and solutions at the same time. Now, you might be wondering, how do we control this superposition and make it work for us? Well, that's where those clever quantum physicists come in. They've devised ingenious ways to manipulate qubits and put them into specific superpositions, allowing us to perform complex calculations that would leave classical computers in the dust. Quantum entanglement, spooky action at a distance. But hold on, there's another mind-bending phenomenon in the quantum world that takes things to a whole new level of weirdness. And that's quantum entanglement. Einstein himself called it spooky action at a distance, and for good reason. Imagine two of our spinning qubits far apart from each other. When these qubits become entangled, it's like they're connected by an invisible thread, no matter how far apart they are. Measuring the state of one qubit instantly determines the state of the other, as if they're communicating faster than the speed of light. Now, before you get any ideas about breaking the cosmic speed limit, it's important to note that entanglement doesn't actually involve information traveling faster than light. It's more like these two entangled qubits are two sides of the same coin, even when separated by vast distances. This interconnectedness, this spooky action at a distance, is what gives quantum computers their true edge. By manipulating and measuring entangled qubits, we can perform operations on multiple qubits simultaneously, exponentially increasing their computational power. It's like having a team of synchronized swimmers moving in perfect harmony to achieve a common goal. Entanglement is a powerful resource in quantum computing, allowing us to tackle problems that would be impossible for classical computers to even dream of solving. It's like having a secret weapon, a quantum cheat code, that unlocks a whole new realm of possibilities. Alright folks, let's break down the key differences between classical and quantum computing. Imagine you have a massive library filled with books, and you need to find one specific piece of information. A classical computer is like a diligent librarian who meticulously checks each book one by one until they find the information you're looking for. Now, a quantum computer, on the other hand, is like having a team of superpowered librarians who can magically access all the books simultaneously. They can instantly scan through the entire library, exploring multiple paths at once, and pinpoint the information you need in a fraction of the time. That's the fundamental difference between classical and quantum computing. Classical computers rely on bits, which can be either a 0 or a 1, like a light switch that's either on or off. Quantum computers, however, harness the power of qubits, which can exist in a superposition of both 0 and 1 simultaneously, like a dimmer switch that can be in multiple states at once. This fundamental difference in how they process information is what gives quantum computers their edge, allowing them to tackle problems that would take classical computers billions of years to solve. It's like comparing a bicycle to a supersonic jet, both modes of transportation, but operating at vastly different speeds and scales. Section 2. The quantum advantage: speed and scale. Think of it this way. When faced with a complex problem, a classical computer is like trying to find a needle in a haystack by meticulously sifting through each piece of hay. A quantum computer, with its ability to explore multiple possibilities simultaneously, is like using a powerful magnet to instantly pull the needle out of the haystack. This quantum advantage becomes even more pronounced as the problems we're trying to solve grow in complexity. For certain types of calculations, such as simulating molecules or breaking encryption codes, quantum computers offer an exponential speed-up over classical computers. Imagine trying to model the behavior of a complex molecule like caffeine. A classical computer would need to consider every single electron and atom, a task that quickly becomes computationally intractable. A quantum computer, however, could leverage superposition and entanglement to represent all possible states of the molecule simultaneously, leading to much faster and more accurate simulations. This ability to handle massive amounts of data and perform complex calculations at unprecedented speeds is what makes quantum computing so exciting for fields like drug discovery, material science, and artificial intelligence. It's like having a superpowered brain that can process information and solve problems in ways we never thought possible. Section 3. Different tools for different tasks. Now, before we get carried away and declare classical computers obsolete, it's important to remember that quantum computers are not meant to replace classical computers entirely. They're different tools for different tasks. Think of it like this. You wouldn't use a sledgehammer to hang a picture frame, just like you wouldn't use a paintbrush to demolish a building. Similarly, classical computers excel at everyday tasks like browsing the internet, writing emails, and streaming videos. Quantum computers, on the other hand, are better suited for tackling highly specialized problems that involve complex calculations and massive data sets. They're like the high-powered telescopes of the computing world, allowing us to peer into the fundamental nature of the universe and unlock solutions to some of humanity's greatest challenges. In the future, We can envision a world where classical and quantum computers work together, each playing to their strengths. Classical computers can handle the day-to-day tasks, while quantum computers tackle the grand challenges in medicine, material science, and beyond. So, while quantum computers are not about to replace your laptop anytime soon, they represent a paradigm shift in computing, opening up a universe of possibilities that we're only beginning to explore. Section 1. Revolutionizing industries, from medicine to materials. Now let's shift gears and talk about how this revolutionary technology is poised to transform various industries. Imagine a world where diseases are diagnosed and treated with unprecedented precision, where new materials are designed at the atomic level, and where financial models can predict market trends with incredible accuracy. This is the promise of quantum computing, and it's already starting to become a reality. In the field of medicine, for instance, quantum computers could revolutionize drug discovery. Imagine being able to simulate the behavior of complex molecules like proteins, which play a crucial role in virtually all biological processes. With quantum computers, we could design drugs that precisely target specific diseases, minimizing side effects and maximizing effectiveness. This could lead to breakthroughs in the treatment of cancer, Alzheimer's, and other debilitating diseases that have plagued humanity for centuries. But it's not just medicine that stands to benefit from this quantum revolution. In material science, quantum computers could help us design materials with tailor-made properties. Imagine creating super-efficient solar cells, lightweight yet incredibly strong alloys, or even self-healing materials that can repair themselves at the molecular level. The possibilities are truly endless. By harnessing the power of quantum mechanics, we could usher in a new era of materials that are stronger, lighter, more durable, and more sustainable, revolutionizing industries ranging from aerospace to electronics. Section 2. Cracking the code, quantum cryptography and security. Let's move on to another critical application of quantum computing: cryptography. In today's digital age, protecting our data and communications is more important than ever. From online banking to sensitive government information, we rely on encryption to keep our secrets safe from prying eyes. But here's the thing. Many of the encryption methods we use today rely on mathematical problems that are difficult for classical computers to solve, but could be cracked wide open by powerful quantum computers in the future. That's where quantum cryptography comes in. By harnessing the principles of quantum mechanics, we can create ultra-secure communication channels that are virtually unhackable, even by quantum computers. One promising approach is quantum key distribution, which uses the principles of superposition and entanglement to generate and distribute secret keys between two parties. Any attempt to intercept or eavesdrop on the communication would inevitably disturb the delicate quantum states, alerting the legitimate users to the breach. With quantum cryptography, we can ensure the privacy and security of our data in a post-quantum world, safeguarding everything from financial transactions to national secrets. It's like having an unbreakable quantum shield, protecting our digital lives from even the most sophisticated cyber attacks. Section 3. A quantum leap for artificial intelligence. Now, let's talk about how quantum computing can supercharge another rapidly evolving field: artificial intelligence. AI relies on algorithms, which are essentially sets of instructions that tell computers how to learn from data and make decisions. Classical computers can handle some pretty impressive AI tasks like image recognition and natural language processing, but when it comes to tackling more complex problems like understanding human emotions or developing truly intelligent machines, they hit a wall. That's where quantum computing comes in. With their ability to process massive amounts of data and perform complex calculations at speeds unimaginable for classical computers, quantum computers could unlock new frontiers in AI. Imagine training AI algorithms on quantum computers, allowing them to identify patterns and make connections that would be impossible for classical computers to discern. This could lead to breakthroughs in areas like drug discovery, material science, and even our understanding of the human brain. Quantum computers could also pave the way for more sophisticated and efficient machine learning algorithms, enabling AI systems to learn faster, adapt to new situations more effectively, and solve problems that were previously considered unsolvable. Section 4. the quantum future, what lies ahead. As you can see, the potential applications of quantum computing are vast and varied, spanning multiple industries and scientific disciplines. From revolutionizing medicine and materials science to enhancing cryptography and supercharging artificial intelligence, quantum computing has the potential to reshape our world in profound ways. Of course, this technology is still in its early stages of development, and there are many challenges to overcome before it becomes mainstream. But the progress we've made in recent years is incredibly exciting, and the future of quantum computing is brimming with possibilities. Who knows what incredible breakthroughs await us in the quantum realm? Perhaps we'll discover new particles, unlock the secrets of the universe, or even create artificial intelligence that surpasses human capabilities. Only time will tell, but one thing's for sure. The quantum revolution is here, and it's going to be an exciting ride. Now, before we get carried away with dreams of quantum supremacy, let's take a sobering look at the current limitations of this revolutionary technology. Building a quantum computer is no walk in the park. It's like trying to assemble a watch using microscopic gears made of soap bubbles, incredibly delicate and prone to collapsing at the slightest disturbance. One of the biggest challenges is maintaining the stability of qubits. Remember superposition, that magical state where qubits can be both 0 and 1 at the same time? Well, it turns out that superposition is a very fragile state, easily disrupted by external noise and interference from the surrounding environment. Think of it like trying to balance a spinning top on a bumpy train ride. The slightest jolt or vibration can send the top tumbling down, losing its delicate balance. Similarly, even the tiniest fluctuations in temperature, electromagnetic fields, or vibrations can cause qubits to lose their superposition, leading to errors in computation. And if maintaining the stability of a single qubit wasn't challenging enough, imagine trying to do it for hundreds or even thousands of qubits, which is what we'll need to build truly powerful quantum computers. Scaling up the number of qubits while preserving their stability is a monumental task that keeps quantum engineers awake at night. This sensitivity of qubits to their surroundings is a phenomenon known as quantum decoherence, and it's one of the biggest hurdles in the quest for practical quantum computers. It's like trying to choreograph a ballet on a vibrating platform. The dancers, or qubits, are constantly being thrown off balance, making it nearly impossible to maintain the delicate choreography of quantum computation. To combat decoherence, scientists are developing ingenious techniques to isolate qubits from their environment, like supercooling them to temperatures colder than deep space, or trapping them in magnetic fields. Imagine building a soundproof, vibration-free chamber deep underground, shielded from any external disturbances. That's the level of isolation we're talking about. But despite these efforts, decoherence remains a significant challenge, limiting the amount of time qubits can maintain their quantum properties and perform computations. It's like trying to hold your breath underwater. Eventually, you need to come up for air. Similarly, qubits can only maintain their quantum states for a limited time before decoherence sets in, introducing errors into the computation. Overcoming decoherence is crucial for building fault-tolerant quantum computers that can perform long and complex calculations without succumbing to errors. It's like trying to build a sandcastle that can withstand the crashing waves. It requires ingenuity, precision, and perhaps a little bit of quantum magic. But the challenges don't end there. Even if we manage to build stable and scalable quantum computers, we still need to figure out how to program these mind-boggling machines. Writing software for quantum computers is a whole new ballgame, requiring a completely different way of thinking about algorithms and computation. Classical computers use programming languages like Python and Java, which are based on the principles of classical logic and Boolean algebra. Quantum computers, however, require specialized programming languages that can describe and manipulate the bizarre world of quantum mechanics, with its superpositions, entanglements, and probabilistic nature. It's like trying to write a musical score for an orchestra of cats. You need a completely different set of notations and instructions to get them to play in harmony. Similarly, quantum programmers need to think in terms of quantum gates, quantum circuits, and quantum algorithms to harness the power of these revolutionary machines. Developing quantum software is a nascent field, and we're only just scratching the surface of what's possible. It's like exploring a vast, uncharted territory, with endless possibilities for new discoveries and innovations, but it also requires a new generation of quantum programmers, fluent in the language of qubits and entanglement, to unlock the true potential of these extraordinary machines. Despite these current limitations, the future of quantum computing shines brighter than a supernova. Scientists and engineers are working tirelessly, pushing the boundaries of what's possible. Imagine a future where quantum computers are as commonplace as smartphones, unlocking solutions to some of humanity's most daunting challenges. One exciting area of development is fault-tolerant quantum computing. Remember those delicate qubits prone to errors from decoherence? Well, researchers are exploring ways to create quantum computers that can correct their own errors, much like our bodies can repair damaged cells. Think of it like this. Imagine building a bridge where, if one beam weakens, the surrounding beams automatically adjust to compensate, keeping the bridge stable. That's the idea behind fault-tolerant quantum computing, creating systems that can gracefully handle errors and continue operating reliably. Another promising avenue is hybrid quantum classical computing. Remember, quantum computers aren't meant to replace classical computers entirely. Instead, we can envision a future where these two types of computers work together, each playing to their strengths. Think of it like a team of superheroes, each with their unique powers. Classical computers can handle the day-to-day tasks, like data storage and communication, while quantum computers swoop in to tackle the really tough problems, like simulating molecules or breaking encryption codes. As quantum computing technology matures, we can expect to see a wave of innovation across various industries. In medicine, imagine personalized treatments tailored to an individual's genetic makeup, new drugs designed with atomic precision, and early disease detection that could save countless lives. In materials science, imagine developing super-efficient solar panels that can harness energy from even the faintest rays of sunlight, creating batteries that can store vast amounts of energy, or designing self-healing materials that can repair themselves like living tissue. And in the realm of artificial intelligence, imagine AI systems that can understand and respond to human emotions. Robots that can learn and adapt to new environments with human-like intuition, and virtual assistants that can anticipate our needs before we even ask. These are just a few glimpses into the transformative potential of quantum computing. As we venture further into this uncharted territory, we can expect to encounter both challenges and opportunities that will shape the future of technology and redefine what's possible. The quantum revolution is not merely about building faster computers, it's about expanding our understanding of the universe and harnessing the power of the quantum realm to solve problems that have long seemed insurmountable. It's about ushering in a new era of discovery and innovation that could transform our world in ways we can only imagine. So buckle up and get ready for the ride, because the future of quantum computing is going to be nothing short of extraordinary. As we've journeyed through the fascinating world of quantum computing, from the mind-bending principles of quantum mechanics to the potential applications that could reshape our world, one thing is abundantly clear. The quantum revolution is not a distant dream. It's knocking at our doorstep, ready to redefine the boundaries of what's possible. Imagine a world where diseases are diagnosed and treated with unparalleled precision, where materials are designed atom by atom to exhibit extraordinary properties, and where the secrets of the universe are unlocked through simulations of unimaginable complexity. This is the promise of quantum computing, a promise that is rapidly transforming from science fiction into tangible reality. The road ahead is not without its challenges, of course. Building stable and scalable quantum computers, developing robust quantum software, and nurturing a new generation of quantum experts. These are but a few of the hurdles we must overcome on our quantum quest. But the potential rewards far outweigh the challenges. Quantum computing has the power to revolutionize industries, accelerate scientific discovery, and address some of humanity's most pressing problems, from climate change to disease eradication. It's a journey into the unknown, an exploration of the universe's most profound secrets, and an opportunity to shape a future brimming with hope and possibility. So, as we stand on the precipice of this quantum frontier, let's embrace the unknown with curiosity and determination. Let's continue to explore the mysteries of the quantum realm, push the boundaries of human ingenuity, and work together to harness the transformative power of quantum computing for the betterment of humanity. The quantum revolution is not just a technological revolution. It's a revolution in thought, a paradigm shift in how we approach problems and envision solutions. It's a call to embrace complexity, challenge assumptions, and think beyond the limitations of our current understanding. And as we embark on this exciting journey, I invite you to join the quantum conversation. Share your thoughts, questions, and ideas in the comments below. Let's explore the wonders of quantum computing together, unravel the mysteries of the universe, and shape a future where the impossible becomes possible. Don't forget to like this video if you found it informative, subscribe to my channel for more cosmic adventures, and hit that notification bell to stay updated on the latest breakthroughs in the quantum realm. Until next time, stay curious, keep exploring, and never stop questioning the boundaries of what we know.